Okay. Hi guys, my name is Anurag Bhaisare, TYBSc Physics Department, and we are having our annual event from the Astro Club. So as you know, Astro Club is celebrating 25 years of success and passion towards the outreaching of the astronomy. So as of today is 25 January 2024, and in today we have for the theme of the poster exhibition is the evolution of astronomy. So basically we are going from ancient astronomy to the modern astronomy and all the things that have been through. So as you can see, we are having total 36 posters, and we have various creative models, and the posters, they are very innovative, they are like superb, and the explanation is also very simple that can be understood by the general public. So yes, this you can see the board. And to know more about for the today's event, we will go through the each posters and see what they have to tell about.
So our topic name is ancient astronomy. So how astronomy started, how we look on the sky, क्या instrument बनाए हमने. So we can look out the Samrat Yantra. It's the sundial. We can get the local time. So we are in Pune. We can get the Pune's local time. So in Pune it's around 10. So it's around 9:50. We can see that there. So our time IST time is around 10:40. But there is a difference of 8 degree in longitude. We have to minus 36 minutes. But during the winter solstice, we have to add 9 minutes. So on an average, we are 45 minutes behind the time. So now it's around 10:41. We have to minus 45 minutes. So we get the time around 9:55 to 10 o'clock. So we can get that. It's the 9:30, 10, 9:45. It has crossed the line of 9:45. It's around 10. So it's working. We can see the posters.
Okay, so my name is Anokhi. I'm an FIBSc physics student. So the first poster of our group Ancient Astronomy is Introduction to Ancient Astronomy. Here we tell what is astronomy, and after that we move on to particularly prehistoric astronomy. That is that era during which humans did not even have developed writing. So with the help of these few examples, such as the capturing of a supernova image in Kashmir, and then the representation of the constellation of Taurus in Lascaux caves in France, and after that the representation of the night sky in a circular disc in Germany. And another interesting object is the Stonehenge, which was a circular arrangement of stones, and if you stand at its center on June 21st and look in the northeast, then you can see the sun rise exactly above a particular stone called the heel stone. And all of these were just examples, but then comes the reason why we needed astronomy in our lives. So the most basic reason was for timekeeping, such as using sundials, like using sundials and water clocks for keeping time. And then after that, all our calendars are based on astronomical phenomena. And for navigation also, the pole star was very important to determine our directions in the open sea.
So this poster is about ancient Indian astronomy. So first trace of ancient Indian astronomy we found in Indus Valley civilization during 3300 BC. We found there the seals, some seals which shows here it is the sun, and around it there are 4 animals which shows the cardinal points of the earth. Then here there are 7 structures which represents the stars of this Ursa Major, and these are this is proved by the Indian archaeological site that these are the events. These seals gives the data about astronomy by the help of this fish-like structure that are present here. They proves that these are astronomical data. Then in Rig Veda also in Rig Veda we found, during that time they gave us the speed of light in miles per second. They said that one time the time we take to flip our eyes is nimisha, and in half of a nimish they said that the sun travels 2200 yojanas in half of a nimisha. When we convert it into miles per second, it is 1,89,547, which is approximately equal. Then Aryabhatta proposed the heliocentric model of the earth, and he also estimated the circumference of the earth. Then Brahmagupta made much work on the mathematical work to help the astronomical data. Also, he termed a thing Gurutva Akarshan, which means gravity, and he explained gravity as an attractive force which attracts things towards itself. At the end, we see Bhaskaracharya. In his work Siddhanta Shiromani, he explained about the latitudes and longitudes of the earth, and he found those terms with the help of instruments known as Dhiyantra and Yashiyantra, which resembles with the cross staffs.
Hello guys, my name is Saurav Raut. I am from FIBSC Maths, and like you see, our poster name is Ancient Astronomy. Before you see that these two posters tells about astronomy, how astronomy practice around the world. Like you see in this third poster, Babylonian, Greek, Egyptian, Chinese civilization, how study astronomy. Now around the world, Mayans, Arab, Polynesian civilization also studies the astronomy. In this Mayans are in now times, the Mexico parts is where the Mayans people lives. The Mayan peoples are like so advanced in their calculations. They developed two calendars. The one is Zolkin, is of 260 days, and the second is half of 360 days, like us we use in our days. If you see this calendar, half is that calendar. It consists of 19 months. 18 months are of 20 days, and the last month 19 months is of 5 days. And this picture said observatories El Castillo. Okay, from there they studies. And the second is they studies Venus, which they calculate his calendar from our perspective is of 584 days, which our now modern calculation says that is of 583.92 days. And second is Arab astronomy. If you know that Andromeda galaxy and Crab nebula is discovered by them, and they uses for them sextant and astrolabe and crossstaff, and they also measure the timeline of equinoxes. Then Polynesians peoples developed a celestial navigation for the navigation use, and they find they develop lunar calendars for the tides or the find the relation between the lunar eclipses or lunar moon and the tides. They uses this for fishing. And the second, they uses star compass and wave compass for that their measurements. Okay.
Hello guys, I'm Isha. So I'm going to explain about cross staff. So this is a cross staff, also called as Jacob's staff. It dates back when the Bhaskaracharya first mentioned it in his book about the Yashthi Yantra, also called as Dhi Yantra. So in English it's cross staff. So I just removed this because we need one to calculate one distance. So let me tell you about the use of cross staff. Cross staff is used to find the distance between two stars or the angle between two stars. Also it can find so it was also helpful in the navigation in the old times. So as we are seeing, it's a daytime, there is also one use of it, which is to find the latitude of the current location. So now with the help of this, I am going to find the latitude of Pune. So the actual value of latitude of Pune is 18.5. So let's see what we get from this instrument. So first we have to align this with the eyesight, and this is the adjustable window. So as you can see, there is a tree and there is a green dot on the page of the tree. We are using it for the demonstration purpose. So the top part of the window, I am aligning it with the green dot, and the below part I am aligning it with the tree. A tree is a base. Alright, so yeah, so as I have aligned, we have found one value here. So this value is between 34 and 38. So we have to divide it by 2, because this is a small portion of the cross staff. There are 3 windows, and we divide this value 36 by 2, which is 36 divided by 2, which is 18, and that how we get the latitude of Pune. Thank you.
Good morning everyone, I'm Suresh Singh Pawar, and this is our group discovery of EM spectrum and its applications that we've discussed in our posters and in our models. You might have learned about the roots of astronomy in the previous posters. Let's take a step ahead and look at the different discoveries related to EM spectra and all its applications. At first, we have some basics in my poster. I'm sure you're familiar with oscillations and time period, that concept. Applying that concept, let us see what a wave is. A wave basically is a disturbance in the medium which causes the transfer of energy from point A to point B without changing the mean positions. That is, if energy is being transferred from point A to point B, the mean position remains fixed. That is, energy gets transferred from point A to point B and it returns to its mean position. That was about a wave. Let's take a look at the diagram of a wave. The highest point of a wave is the peak, lowest point is the trough. The distance between two adjacent peaks or two adjacent troughs is the wavelength. Wavelength describes various properties of a wave, which we'll discuss in the next poster. Then we have the amplitude, which is the maximum displacement of a particle from its mean position. Next up, we have the types of waves. At first, we have longitudinal waves. Longitudinal waves, the main characteristic is that the direction of propagation of the wave is same as the direction of the oscillation of the particles. Best example of this would be a spring. That is, the two main words are rarefaction, compression. The best example, also another example, would be sound. Heading on to transverse waves. In these waves, the direction of propagation is perpendicular to that of the direction of oscillation of the particles. To explain this, we have a model here. If we consider electromagnetic waves and in particular light to be an example of transverse waves, this model shows the 3D working model of how light would propagate. If I tap here, this shows the propagation of light in real life. Also, if we consider the middle tape to be the light, the Y component here would be the magnetic field, the horizontal component would be the electric field. Hence, this poster describes the various how light propagates and how electromagnetic field propagates. The last segment of the poster is light, which I just demonstrated. It is just magnetic and electric field oscillating perpendicular to each other. So that's all for my poster. You'll learn about the discovery of EM spectrum in the next few posters.
Hello, I'm Pranjal. I'm first year BSc Physics student. So this poster is about discovery of electromagnetic spectrum. As you have learned about light and waves in the previous poster, now we'll see what are electromagnetic waves. So basically, electromagnetic waves are transverse waves. They are formed when electric field couples with magnetic field. And since these waves are transverse waves, electric field and magnetic field oscillate perpendicular to each other. Now the next is how they were discovered. In 1887, Heinrich Hertz demonstrated the existence of electromagnetic waves, and in his experiment, he applied high voltage current to the end of two wires which created spark, causing electromagnetic waves. Now we'll see the different types of wave. The first one is radio waves. They were discovered by Heinrich Hertz, and these waves have greatest wavelength and least frequency because frequency and wavelength are inversely proportional to each other. So these waves are used in mobile, radio communication and broadcasting. The next is microwaves. Microwaves were discovered by James Clerk Maxwell, and they are used in radar and speed guns and all. The next is infrared rays. They are used in physical and heat therapy. The next is visible light. It was discovered by Isaac Newton using a prism. And the next is UV rays. Ultraviolet rays, the main source of it is sun, and they are used in eye surgery. The next is X-rays. They are used to detect fracture in the bones. And the last one is gamma waves. It was discovered by Paul Ehrlich-Wheeler, and they have greatest frequency and least wavelength, and they are used to destroy cancer cells. So this was all about my poster. Now you will see black body radiation and spectroscopy in other two posters. Thank you.
Good morning everyone. I am Virendra Raskatla of class FIBSc Physics, and today I will be presenting a poster on black body radiation. In the previous poster, you learned about what are EM waves and the discovery of EM waves. In this poster, we will learn about what is a black body radiation. So now let's understand what is a black body. So black body is an idealized surface that absorbs all the incident radiant energy that falls on it. And the examples of black body are rare in nature, but celestial objects like stars are often considered close approximation of a black body. Sun, for instance, is considered as a black body because it emits radiation across a broad spectrum and absorb nearly all the radiant energy that falls on it. Now let's understand what laws are governed in blackbody radiation. So now let's understand what is the Wien's displacement law is. So Wien's law states that the blackbody radiation has different peaks of temperature that are inversely proportional to the wavelength. So as the temperature increases, wavelengths shift towards the smaller wavelength. So now let's understand what is the Rayleigh-Jeans law is. So Rayleigh-Jeans law states that the intensity of a black body is directly proportional to the temperature and it is inversely proportional to the wavelength raised to the power 4. Now let's understand what is the Stephen-Boltzmann law is. So Stephen-Boltzmann law states that the energy emitted by a black body is directly proportional to the temperature. So now this is about my poster. Now in the next poster you will learn about the contribution of spectroscopy and astronomy in the EM spectrum. Thank you.
Hello, I'm Nyanda Kulkarni, SY BSc Physics student, and my poster is about spectroscopy and astronomy. So let's first understand what spectroscopy is. It is actually a study of interaction between the matter and the electromagnetic radiation, and when this happens, it produces a spectrum, and the study of this spectrum is called as the spectroscopy. So there are two types of spectrums, continuous and discontinuous, further divided into emission and absorption. So what happens in emission and absorption spectrum is electrons continuously need a transition energy state to travel from back and forth. So what happens in emission spectrum is it goes from the higher energy level to the lower energy level, and while doing this they emit energy of h nu. So nu represents frequency, so that's why they only emit certain frequencies. Same happens in absorption spectrum, just the opposite way. It is going from the lower energy state to the higher energy state, and while doing this it absorbs certain energy of a certain frequency, and that is what we see, absorbed frequency. Next we have the Raman spectroscopy, which was given by C.V. Raman on the topic of scattering. So when the frequency of the scattered photon is different from the incident photon, it is called as Raman scattering. So next we have is astronomical point of view from spectroscopy. So for just say, let's consider this as a planet and I am the host star. So what it will do is, if it's revolving around me, you can hear the pitch shift. So pitch will decrease and increase frequently, and what happens after that is in Doppler's effect, when it's going away from you, the pitch will decrease and so will the frequency, and then that is what is called as redshift. And when it's coming towards you, it is the blue shift, as the pitch and frequency will increase. Next we have is element detection. In this, the absorption of elements takes place from a planet through the through the electromagnetic radiation by stars, and that is what we see as the spectrum. So if the planet is made up of hydrogen, you will see only the Fraunhofer lines of H, and if it's oxygen, you would see O2. And Big Bang theory is just a very famous phenomenon, as a fact that how universe was produced, and redshift is actually evidence that it is actually true.
Myself Harsh Mule, I am SYBSc student of physics. You all have learned what is black body. So we are here demonstrating a small model of black body. So as you learned that black body absorbs all the radiation incident on it. So we have taken the concept of this model from the Ferris black body construction. He took a cavity and planted by lamp black or venta black from inside, which has highest absorptivity. And he made a small hole to incident a radiation. When a radiation is incident on the inside walls, it gets absorbed up to which its absorptivity, and other part is emitted and it gets reflected by other walls. So multiple reflection happens inside this. So here we are demonstrating it. So you can see from this. Lasers, you can see laser beam inside. Okay. So we have used a laser source here to incident radiation, and internally we have fitted mirrors instead of black color.
Hello everyone, myself Arpit Kothur from FY BSc Physics, and I believe you have all come from the explanation from the EM spectra. So now after the invention of the discovery of the EM spectra, we move towards the discovery of the telescope itself, which was the next major advancement in astronomy. Now there are records of the telescopes existing in 15th and 16th century as well, or the devices similar to telescopes. The first modern telescope was invented in the year 1608 by spectacle maker Hans Lippershey. Now all the early telescopes used Lippershey's configuration, and they were used for military purposes such as spying, surveillance, etc. That was until Galileo Galilei came around, the famous Italian scientist, who made his own telescope using uncertain descriptions of Lippershey's telescope and made it better. It had around 3 times more magnification than the Lippershey telescope, and he pointed that telescope to the sky. He used it to observe various celestial bodies such as the moon, Jupiter, where he observed the 4 moons of Jupiter, which are called the 4 Galilean moons in his honor, as well as sun, where he became the first person to observe sunspots. Then in 1611 comes Johannes Kepler, and he suggests an edit in the Galilean configuration. Now Galilean configuration uses a convex lens as the objective lens and a concave lens as the eyepiece. What Kepler suggested was, instead of using a concave lens for the eyepiece, let's use a convex lens. What that allowed was better magnification as well as better eye relief. Now both of these telescopes had a problem called as chromatic aberration. Basically, when light travels through a lens, the lens acts as a prism and the light gets divided into the spectrum. And because the mean deviation angle between red and blue is the highest, we see halos of red and blue around any objects. So to combat the problem of chromatic aberrations, in 1668 Sir Isaac Newton came up with a reflecting telescope which used mirrors instead of lenses. Now Newton used a concave mirror which focused its point onto a focus, where there is another mirror which then reflected into the eyepiece. Now with this we conclude the first poster, and we will move on to the next poster, that is types of telescopes.
So hello everyone, my name is Meet Mehta. I am from the physics department and Astro Club. So basically we'll study the second poster. First we saw the discovery of telescope. Now we'll see the types of telescopes and their working. So basically we have 3 types of telescopes: a refractor, a reflector, and a Maksutov-Cassegrain telescope. So basically a refractor telescope is a telescope which has a lens in front of the telescope. It is a plano-convex lens. So basically the light travels inside the telescope, gets bent, and then we can finally it focuses around here, so we can see it through the eyepiece. So this telescope was good enough, but it had one problem. That was it had chromatic aberrations. So basically what are chromatic aberrations? Basically when a light is passed through a lens, it as we know, light is made up of wavelengths. So each wavelength has a different refractive index. Hence when the light is passed through the lens, each wavelength of the light is bent in a different manner. Hence the blue and the red light of the spectrum is bent more. Hence we see halos of blue and red around the object we are observing. So that was a big problem. Hence we shifted to the reflected telescope. The reflected telescope is basically a telescope which uses mirrors instead of lenses. Hence the working of this telescope is there is a spherical mirror around here and a plane mirror around here. So basically when the light comes inside this telescope, it is bounced off the spherical mirror, it comes to the plane mirror, here it focuses, and then we can finally see it through the eyepiece after reflecting. So this telescope allowed us to have images without any chromatic aberrations. Hence this telescope is very good. But we made another telescope called the Maksutov-Cassegrain telescope. This telescope was basically best of both worlds. It used lenses as well as mirrors. So basically the light would travel through the lens, come to the mirror, and then finally reflect back again at the secondary mirror and go to the eyepiece. So basically these are the 3 types of telescopes, and there are 2 types of mounts on which we are mounted. The first one being an alt-azimuth mount and second one being an equatorial mount. So this is the second poster. Thank you.
Hello guys, I am Srunal Marathe, SY BSc Physics. So today we are looking at the ray diagram model of Maksutov-Cassegrain telescope. So as you know, this is the most efficient telescope as of use now. So this is a combination of both lens and a mirror. So what happens is light comes in through this, which is a concave lens of a very low power. Then the light goes to the part, this is a spherical mirror which reflects the light onto this small spherical mirror, and then from this mirror the light finally goes to the eyepiece and where you see the object. So the advantage of this mirror, this telescope, is that it can be fitted into a shorter length of telescope compared to the other 2 telescopes. And because the light travels for much farther length, it has a better resolution and it's also cost effective.
Hello, my name is Sanjit Kushe and I am from FY BSc Physics. In the previous poster, we saw the types of telescopes and how they are working. And in this telescopes, I will walk you through the advancements and achievements of our telescope history. So as you can see, in the first poster you have learned that we were facing a problem of chromatic aberration. So 100 years after the first telescope was made, we came up with a solution of achromatic lenses. So basically in an achromatic lens, convex lens is taken and a concave lens is taken. So the light, when the light passes through the convex lens, it bends in a positive manner, and when the light passes through the concave lens, it bends in a negative manner. So the positive and the negative becomes neutral. After that, we come on to 1845, where the first observatory was set up in Ireland by William Parsons. And then in 1917, the 100-inch Hooker telescope was introduced on Mount Wilson in California. The thing about this is that Edwin Hubble used this telescope to observe two specific galaxies that were moving apart from each other. Now this allowed him to think about that the universe is expanding, and so the universal expansion theory came to life. After that, in 1944, Dmitry Matsutov made his Cassegrain telescope, which was explained in the previous poster. In 1948, Hale reflector telescope was introduced, and it was the first telescope made for astrophotography. What happened was they removed the eyepiece and put a photographic sensor on it, so the whole telescope was made into a big camera. After that, in 1965 came the Dobsonian mounts. So the thing about this was that it was a type of altitude azimuthal mount. What it did was there were two discs that would slide onto each other, and it gave the telescope a 360-degree movement. And then there would be two poles which would hold the telescope like this, and it would move in a seesaw movement. So it was up, down and 360. After that, in 1990, we sent a telescope in space. It was named the Hubble Space Telescope, and that was quite a huge feat for us, as we tackled the whole atmospheric error problem. After that, in 2001, the Astronomical Observatory came along, Indian Astronomical Observatory, which is in Handley, Ladakh. After that, in 2007, we came on to Gran Telescopio Canarias. This is currently the record holder for the largest telescope, and is located in Spain. Then we come on to 2021, where we were introduced by the James Webb Space Telescope, which is currently the best space telescope we have in space, and it has been sending us a lot more precise data than Hubble Space Telescope. Moving on, in the next poster, we'll see the prominent telescopes of the modern age.
So hi everyone, my name is Manas Gosavi. I'm a second year student. So in previous posters we have learned how telescopes got advanced and advanced. We have seen the timeline in the previous posters. Now in the next poster we have prominent telescopes of modern age. In this poster we have already seen the 100-inch Hooker telescope, Hale Observatory, Indian Astronomical Observatory, Hubble Space Telescope and James Webb Telescope in the previous posters. The important telescopes which we are going to learn here are the extremely large telescope and the 30-meter telescope. These two telescopes are currently in inbuilt phase. They haven't been completed or haven't started their building. These two telescopes are currently fighting for which telescope will be the largest telescope in this world. So the 30-meter telescope will be built in Hawaii, and it is an organization of 30 plus countries which will be taking part. India is also a part of this this organization. Extremely large telescope similarly is being built in Chile. Okay. Then Indian Astronomical Observatory, the prestigious, you can say, Indian Astronomical Observatory, which is situated in Hanle, Ladakh, and also Dark Sky Reserve around Hanle was recently been stated by the Indian government. And the Hubble Space Telescope and James Webb are the two prominent space telescopes which we have seen in the previous, so I won't discuss about it much further. And finally the Arecibo Radio Telescope, which is a connection link for the next group, which is radio astronomy and radio telescopes. Thank you.
My name is Siddhant Mutha. Our team is radio astronomy, and this is optical astronomy. So in my poster, a journey to radio astronomy. In 1888, Hertz discovered radio waves. In Second World War, the radar technology developed, and
it's advanced the radio astronomy. In 1944, Carl Jansky discovered that the celestial body emit radio waves. So therefore we started radio astronomy. Advantage of radio astronomy over the optical astronomy. So basically what does happen? Visible light जो है, visible light blocked by some dust clouds, so we can't study the objects behind that. So but radio waves can penetrate through that object, and we can study more objects behind that. So that's why we use radio waves for study more phenomena of our cosmos. So in 1951, 21 centimeter hydrogen light discovered by mapping hydrogen cloud. In 1960s, pulsar detected by using radio waves, and in 1965, cosmic microwave background radiation also detected by, and this reveals the universe, how universe is formed and how universe is going.
Hey there, my name is Om Yadav. In the last poster you saw how the radio waves were discovered. In this poster you're gonna see the detection and the methodology and the instrumentation of the radio waves. So radio waves are something called electromagnetic waves. So when the radio waves falls on this is called as GMRT. GMRT stands for Giant Meter Wave Radio Telescope, and when the radiation falls on this, it gets received at a focal point. There is a receiver at the focal point. When this radiation gets received, it converts into an electrical signal using something called electromagnetic induction. So after we obtain an image, we have to do something called Fourier transformation to analyze the data, to analyze to process the image. So Fourier transform means simply it's like it picks up the most dominant dominant frequency, and it shows up there. And there is something called antenna backend system afterwards, which is like, in brief, antenna backend system is something like, first we do is called data acquisition. Data acquisition is like we receive the data in this context. Data means radiation, and after that we do calibration. Calibration is like transforming this radiation into electrical signal. It's like transformation in simply. Flagging is like we remove the unwanted clutter from the data we receive. Then there is visibility. Visibility in simply we can say this like this. It's like this measure of the strength of the signal. Is like visibility. It is visibility, and then we proceed for image analysis. There are a lot of types of antenna, but two of them here would be Yaji-Uda. If you have seen, there are old types of antenna over the TVs, and that's what called Yaji-Uda. And there are parabolic reflector like this. That's ASRT. You must be wondering why ASRT has like this the total, and why this has like the strings. The difference is the reason is this M. M stands for meter wave, and imagine this whole plate like a tennis racket. When a ball falls on the tennis racket, doesn't matter how hard you push it, it won't get through it. So that's the same concept. When a radio wave falls on this, it won't get through it. Yeah, so that's the concept. Thank you.
Hi everyone, my name is Anuja and I am an SYBSc student. And as you learned in the previous poster, we talked about different types of antennas and how an image is created using the antennas. In this poster, I'll be telling you about the techniques of radio interferometry. Radio interferometry is basically used to capture images, to capture high resolution images of distant celestial objects. So there are two types of radio interferometries. One is VLBI and second is aperture synthesis. VLBI stands for very long baseline interferometry. So as the name suggests, the baseline is the distance between two telescopes, and interferometry is the phenomenon which is based on interference. What happens is when radio signals come from are incident on the parabolic dish from a source from infinity, they converge at a point on the dish which is known as the focus. And these radio signals are then transmitted and stored in hard drives. So these hard drives are actually physically transported to central facility such as the Massachusetts Haystack Observatory, and then to the Max Planck University, where the data is actually correlated and synchronized using various supercomputers. And these are lots and lots of numbers basically. So the scientists use supercomputers to correlate the data and synchronize them, and then that is how they create the image. Several examples of VLBI are the Event Horizon Telescope and the European VLBI network.
And in the same way, we can consider GMRT, which uses aperture synthesis, but on a smaller scale. That's it.
I'm Athar Firki from FIBSC. In previous poster, we studied about the techniques and techniques used in radio astronomy. I'll explain more about the breakthroughs and the radio observatories. So, the event horizon. This is a visual representation of the Event Horizon Telescope. It's international collaboration between a lot of radio observatories and telescopes that are linked. Let's assume them as a virtual telescope that is Earth-sized in order to capture the distant black holes, the radio waves coming from the black holes. The Event Horizon Telescope took this famous image of the M87 star black hole, which is 55 million light years away from us. Apart from this, there are things like cosmic microwave background radiation, which in simpler words is, let's assume the Big Bang. After the Big Bang, when the universe was cool enough for the initial hydrogen atoms to form, the photons could actually pass through the atoms, and that's when we study them on the Earth, we can actually take a peek into 13.8 billions of history of our universe. The GMRT. The GMRT is located in Pune, 80 kilometers north of Pune, and it is a world-class facility to analyze low frequency radio waves, which makes it a very compelling radio observatory for understanding the 21 centimeter hydrogen line, which is emitted by neutral hydrogen in our universe. The Square Kilometer Array, an upcoming international collaboration. It will aim to study distant redshifted celestial bodies, and 1,31,000 of these SKLO, which are tree-like structures with dipoles, are being made in Western Australia, and SK-Mid, 197 parabolic dishes are being made in South Africa for studying cosmic dawn, origin of life, and other such things which Giant Meter Wave Radio Telescope and ETH aim to.
My name is Rohan Singh Bora. I am from SY BSc Physics major. My poster is of Advent of Astronomy. The first poster was Introduction to Astronomy, how Hertz discovered it, how we used it in World Wars. The second one was different type of antennas and how we process images. The third is about interferometry, how we use n number of antennas to increase our angular resolution placed at some distance. And the last one is about Event Horizon Telescope, which was a major breakthrough for all of us. Now we are at ASRT, which is Affordable Satellite Radio Telescope. Okay, so this is basically a dish TV. What happens is it detects high frequency radio waves. All the radio waves that comes to it bounces back to this feed. This feed consists of a probe, because the radio waves comprise of electromagnetic waves, which basically means they have oscillating electric and magnetic fields. The probe is a metal conductor. Due to having a oscillating magnetic field, there is a induction of potential in the probe, which is in the form of potential, and this potential which is induced here is passed on to this coax cable to our appliances. This is ASRT.
Hello, I am Yash Deshmukh. So I am here to demonstrate you the Libra, which was made by our super seniors in the competition of SWAN, which was jointly conducted by RRI and GMRT. So basically Libra stands for linearly polarized indigenous broadband radio antenna, where we can see it has the two planes. This is the XZ plane and this one is the YZ plane, where if we consider one plane, we can see a bow tie antenna. Our seniors tested many types of antennas in FECO software to get an optimum wavelength range. So what we saw with the bow tie gave the most significant range. Also, the task given to our seniors was that to make an antenna within 80 to 320 megahertz and in an area of 1 by 1 meter. So here we can see the three bow ties are combined
to make an broadband antenna. As we can see, 80 to 320 megahertz is very broad band. Here the inner one is the higher frequency band, the middle one is medium frequency, and the outer one is lower frequency. So this is what our seniors made. Also its background electronics is remaining to be constructed, which is done by our seniors, and so it is under ongoing development, which we can see where somewhere in India if we get successfully developed and represented. Thank you.
Hello, myself Muskan Patwa. In previous poster you will saw why we have to go to space, because we know the earth-based observatories like radio telescope. Now we will see the earth-based observatories like satellites from the space. So first poster is all about why we have to go to space. There is EM spectra, and most of the component of EM spectra are not able to penetrate the atmospheric hindrance, and that's why we have to go to space, because they are not able to come to the ground, and if they don't come to ground, we will not able to observe that spectrum and the lights of EM and the components of that EM spectra. So there are the 7 components of the EM spectra, like radio wave, microwave, infrared waves, visible light, ultraviolet waves, X-rays and gamma rays. So in the 7 spectra, some part of the radio waves are able to penetrate to the atmosphere and come at the ground. So that for that reason we can observe the radio waves with the help of radio telescope. Microwaves are not able to penetrate the atmosphere, that's why we can't observe the microwaves from the ground. Infrared waves are also not able to come at the ground, because they literally absorb they literally absorb all the energy in the ionosphere, that's why they are not able to come to the ground. Next are the visible, so we can see all of the part of the visible light because it penetrates through the atmosphere and we can see it. We know about the rainbow. The next is ultraviolet waves, so some part of the ultraviolet waves are able to penetrate to the atmosphere and we can see it from the ground, and most of the part are not able to come, but they form the ozone layer in the ionosphere. X-rays and gamma rays mainly not able to penetrate the atmospheric layers, and we can't observe them from the ground. That's why we have to go to space to observe those rays which are not able to come to the ground, and we want to know more about them.
Good afternoon, I am Mahi from FY BSc Physics, and now I will be explaining this poster on Lagrange points. So as you saw in the previous poster why we go into space, we will now talk a little bit about how we go into space. And to understand this, there is a branch of physics known as orbital mechanics, and that is what we use to send satellites and different spacecrafts into space. So if we throw a ball at an angle, we know that it will go in the parabolic path. We call it projectile motion, and usually the curvature of the earth doesn't really come into play because the distance is not that much. Now imagine if we throw the ball so fast and so high that the curvature of the earth actually becomes irrelevant. So now every time the ball tries to fall down, it can't, because the earth is curved and it goes forward, and in such a way it forms an orbit around the earth. So that's how we send certain objects into space. Now we have Lagrange points, which have recently become more relevant because of Aditya L1. Aditya L1 is placed on the L1 Lagrange point. So there are 5 Lagrange points, and these are basically equilibrium points. So any object placed at this point will remain in its position. So the gravitational forces and the centrifugal forces acting on it will cancel out and the object is stable. L1, L2 and L3 are known as unstable Lagrange points, and L4 and L5 are stable Lagrange points.
Hello, my name is Zoe Mahajan. I am first year physics. The poster I will be explaining is all about Earth and lunar missions. As in the earlier poster, you also about Lagrangian points. We move on to the Earth and lunar missions. Now basically, the Earth orbit, it is divided into 3 different parts. The first is the lower Earth, second is the medium Earth, and third is the higher Earth. Now all the satellites which are used for geographical features and study of them, they all are placed in the low Earth orbits, basically because they are very nearer to the Earth's surface and they give high resolution images. The next is the telecommunication satellites. Now the telecommunications satellites, they are placed in the medium Earth orbits, basically because the radio signals should not be affected by the hindrance which are placed in the lower Earth. That is why we move on to medium Earth. Next is the GPS. Now basically we all use GPS in our daily lives, right? So GPS is basically those satellites are placed in the high Earth orbits. Now I'll tell you how the GPS works. So basically there are 24 satellites which revolve around the Earth, and they constantly send radio signals. And when we on our location on the Earth, as our phone acts as the receiver of those signals, and the time is measured till which the radio signal comes to our phone, and we multiply it with the speed of light, which gives us the distance between the satellite and our location. So basically that is how GPS is used. Next is the lunar missions. Lunar missions is, you can see the Luna series. Luna 2 was the first man-made object to land on the moon. It was about Russia. And Apollo missions, which are from NASA, it carries out the scientific program exploration of the moon.
So hello everyone, I am Shivraj Kanse, and in previous poster you have gone through our GPS and lunar missions. So here come our Chandrayaan. So you all have a basic idea about what Chandrayaan is. So basically Chandrayaan is a series of lunar mission that was initiated by ISRO. And in 2008, ISRO launched its first ever lunar mission named Chandrayaan, and the launching vehicle for the same was PSLV C-11. And the basic aim of Chandrayaan 1 was to study the lunar activities staying at the orbit. There was a component named MIP in Chandrayaan which did a scientific discovery and told us about water molecules presence in form of ice in south pole of the moon. Since then, various research institutes were there who took keen interest in undiscovered south pole of the moon, and for the same thing in 2019 ISRO come up with Chandrayaan 2. And as we all know, there was some software glitch due to which the connection between the Vikram lander and ISRO headquarters was lost, and to overcome the same thing, in 2023 ISRO came back stronger with Chandrayaan 3, and ISRO became the first ever research institute to do soft landing near the south pole of the moon. And that too within a limited budget of 615 crore, which is even less than our modern sci-fi movies. And we managed to do a limited budget because we used the orbiter of Chandrayaan 2 only. There were certain components in Chandrayaan 3 like propulsion module was there, lander module and rover module, which were designed to work for 14 days. 14 days means half of the lunar day, and they did discoveries like Vikram lander did confirm presence of sulfur, which opens the door for discovery of another minerals too, and Chandrayaan did study of ionosphere, which will help in future to establish lunar communication technology, and drill probe dwelt into the lunar surface and revealed vast 60-degree temperature difference just 8 cm beneath the lunar surface. And you can go through our model for more information about components. Thank you.
Hello, myself Gaurav Kumar, and I am here to talk about Chandrayaan's lander and Chandrayaan's rover. So, ISRO did something very historical in 2023 by having the soft landing over the moon. So, I am here to talk about the components and the research done by ISRO via Chandrayaan. So let me start by talking about the payloads, payloads on Chandrayaan's lander and rover. So first of all, Chandrayaan's lander has this payload known as chaste, which is a drilling technology which flips and drills the lunar surface, and moon के surface के 8 centimeters beneath जाके it figures out the temperature difference. The temperature difference came around 64 degrees Celsius, which is quite astonishing. Moving on, the second component of Chandrayaan is this stick looking like component known as Ramba LB. So this studies the plasma density and on the lunar surface. Moving on, now as you saw that rover come out from this RAM, so onto this RAM there is another component known as ELSA. This component is for the study of lunar seismic activities. So what this does is that when RAM comes down, the these components also with the help of suspensions moves towards the lunar surface and touches the moon's surface and studies the seismic activities over it. Moving on from lander to the rover. In rover, we also have this. We have two components, which studies the composition of the moon's surface and detect various elements and minerals. Moving forward, now let me talk about the communication system which Chandrayaan uses. So you can see, so Chandrayaan basically uses two type of antennas. So firstly, let me talk about TTC antenna. So first of all, you can see this component, and behind this component. All these three components are antennas, specifically TTC antennas. So so how many of you have watched the live landing and launch of Chandrayaan 3? So in that live and so usme you must have seen the graphs of velocity and acceleration, etc. So those were covered, those were projected with the help of TTC antenna. Moving forward, we have a X-band antenna, which gives which is a high data rate structure, which a high data speed, which provides which is used to supply data of images of the moon. Moving forward, Chandrayaan also have a lot of cameras. You can see these two pairs of camera, which is a hazard detection camera, and also this is a lander imager of moon from the behind side. Chandrayaan also has two important cameras which helps in the landing. It actually helps in the identification of the exact landing site, and also below the lander we have thrusters. Also we take precise precautions that our model will look exactly just like the real Chandrayaan. So the positioning of each component is as exact as we could be done. Thank you.
Okay, hello, my name is Vedang, and this this demonstration is to explain orbital mechanics and how we send rockets to space. So if we send a rocket straight up, it is obviously going to fall straight back down. But for that, we actually launch the rocket in a parabola. So if you would see how this rocket gets launched. So as you saw, the bottle took the path of a parabola, but in this small distance we cannot really see the curvature of the Earth. But as you can imagine that as this rocket starts going faster and faster, the curvature of the Earth is going to start coming into play, right? So as the bottle travels a longer distance, the Earth starts curving under it. And if the bottle reaches a critical velocity, after which it is traveling so fast that the gravity is pulling it less than how much it is going forward. So the bottle is going so fast that even gravity is not being able to pull it right down to the Earth. So the curvature of the Earth causes it to basically miss the Earth even when it is in free fall. So this object is basically in a free fall, but also always falling to the Earth in an orbit. So that is why we call it. So that is why we call it an orbit. जहाँ पर वो even if it is into space, it has so much tangential velocity that it continues orbiting Earth even after we cut the thrust.
Good afternoon guys, my name is Labdhi Solanki and I am from TYBSc Mathematics. So previously you studied about the Earth orbits and Chandrayaan and the moon missions. Let's go a step further into the universe towards the sun. So sun is a massive hot ball of plasma inflated and heated by energy produced by nuclear reactions at its core. So the main reasons to study sun are it is a major energy source for Earth, for understanding various solar processes, for formation of solar system, to predict space weather, and to better understand how the stars work. Okay, moving on, sun is a layered structure. It has various layers. The innermost is the core, where the nuclear fusion reactions happen. Further, next is the radiative zone, where the photons radiate outwards. Next is the convective zone, where convection cycles happen. Next is the photosphere, which shows granules on it. After photosphere, there is a chromosphere, which is only visible during solar eclipses, and then there is corona. These are the 6 layers of sun.
Hi, I'm Madhura. I'm a first year BSc Physics major student. This is my poster. So till now we have studied about the structure of sun, why should we study sun, and an overview about the sun. Now I'm going to talk about the magnetic field of sun. So magnetic field of sun is dynamic. It changes over time. So why does it change is the question. That's why we have made this model. The sun rotates on its own axis like any other planetary bodies in the solar system, but sun is not a rigid body. It's a hot ball of plasma. So in different positions, sun rotates in different rates. In the equator, it rotates way more faster than the poles. This is known as the differential rotation of the sun, and that is the reason of the complex movement of magnetic field. The magnetic field shifts from poles to equator and back to poles, that is from poloidal to toroidal and back to poloidal. And in a span of 11 years, the magnetic poles of the sun flip, and it takes 22 years for the poles to come back to its original positions. So because of this, there is a rise and fall of a lot of magnetic activities happening in the sun, and one of them is the sunspots. So sunspots are the cooler, darker regions on the photosphere of the sun. And why does it happen is the question. So it happens when because of the complex movement of magnetic field in the sun, there are places where the magnetic field is so concentrated that the plasma which is coming out of the convective zone couldn't reach the photosphere. So the temperature is cool there, and it appears to be dark because the other part of the photosphere is way more bright. So these are the paths of the sunspot, and there is a rise and fall of sunspots over a span of 11 years, which is known as the 11-year cycle. So in the 11-year cycle, the beginning is the solar minima and the end is the solar minima, where less magnetic activities happen and less sunspot happen. And in the middle, it's the solar maxima, where a lot of sunspot happen. In the mid latitudes, a lot of magnetic activities happen, and a lot of solar flares and a lot of other solar activities happen. So the butterfly diagram is a diagram where we can plot the location and the date of the sunspot, and over a span of 10 years, we get it in the shape of a butterfly. So it's called a butterfly diagram. So that's a brief explanation about my poster. So during solar maxima, a lot of solar activities happen, and in the next poster, Dhadkan is going to talk about it.
Hi, I'm Dhadkan. I'm an SY BSc Physics student, and in the last poster you might have seen the internal processes of the sun and how the magnetic field is dynamic. In this poster and in my very wonky model, you can see a physical representation of the magnetic fields by these, that is represented by these wires, and you can also see a few activities that go on. So these activities are the solar flares that are shown here and the CMEs that are shown over here. Now, in my posters, we talk more about the solar flares and the CMEs. The solar flares and the CMEs or the coronal mass ejections, they are a direct consequence of the magnetic field and the changes in the magnetic field. Solar flares and coronal mass ejections, they happen because of the same reason, magnetic recombination. So these magnetic field lines, they tangle in with each other and they snap and break off, releasing all of the energy and plasma that is traveling in these magnetic fields. So if it is just energy that is released, then it is called a solar flare, and if plasma is also released with the magnetic field, with the energy, then it is known as a coronal mass ejections. These two activities are quite violent towards our satellites and electrical grids. Next, we have the coronal heating mystery. So the way we saw in the first poster how the sun gets colder and colder as we move outwards, the corona actually heats up. There are two theories that could try to explain it. We don't actually know the reason, and they say that all of the processes in the sun, they try to heat up the corona. Next, we have solar winds. Solar winds are basically free winding particles that emit from the corona, that go from the corona, and they travel at very high speeds, creating a magnetic field around the solar system, which protects us from cosmic winds. That was all.
So my name is Gautam Singh, third year student. So in last poster, you will be studying all the activities and the phenomena happening on the sun. Now in this poster, we will be studying how Each phenomenon is observed using various observatories, space-based and earth-based. So we are looking for the first space-based observatories. First one is Kodaikanal Observatory, which is located in Tamil Nadu in Palani Hills. It is working under Institute of IA. It has some of the major telescopes like H-alpha, WORM, twin telescopes and full disk heliograph, photoheliograph. Next thing, we will be studying the solar space-based observatories known as Solar Heliospheric Observatory SOHO. It was launched in 1995 by NASA and ESA joint mission. SOHO is a very old space flight which is actually still working and operational for still after 27 years. It has done its major work in heliosseismology, comet discovery, space weather, studies of solar wind and coronal heating problems, and has taken 20,556 like huge numbers of what we can say the chronograph, or we can say the coronal mass ejections of the sun. Next thing is the Parker Solar Probe. Parker Solar Probe has a particular specific mission to touch the sun, not actually touch the sun, but actually the Parker Solar Probe did visited the outer corona of the sun using Venus flybys. So Parker Solar Probe was launched in 2018 and it has touched the sun in 2021. It has one of few of the very important plasma analyzers like field, sweep, and it measures the magnetic field characteristics of solar particles. Last one is our Indian owned solar mission, which was launched on 2nd September 2023, where we actually visited. So Aditya L1 mission is a joint mission of various institutes and ISRO. So it is located at, first thing, it is located at Aditya L1. Aditya means sun and L1 means the point which will be going to. Second thing, it was launched, so it has 7 major payloads. First one is visible emission line chronograph, which is VLC. Second one is SOOT, solar imaging, solar ultraviolet imaging telescope. Third one is SOLEX, solar low energy X-ray spectrometer. Fourth one is high energy X-ray spectrometers. Aditya L1 wind particle experiment aspects, plasma analyzer package for Aditya L1 and magnetometers.
So hello, my name is Vishwaja. I am from first year BSc Physics and I am going to tell you about the Aditya L1. So basically Aditya L1 was the first ISRO's first solar mission, which was launched in September 2023, and it has a total of 7 payloads. Here we have VELC, which is visible emission line coronagraph, which basically creates a fake solar eclipse kind of around the sun to capture the image of the corona. So basically it blanks out the sun to capture the image of the corona. Then we have SOOT, which is solar ultraviolet imaging telescope. It was made here in Ayuka with close collaboration with ISRO. It captures the ultraviolet narrow images of the photosphere and the chromosphere of the sun. Here we have 2 X-ray spectrometers, Helios and Solexis. Helios is Helios studies the hard X-rays or the high energy X-rays produced by the sun, and Solexis studies the soft X-rays or the low energy X-rays produced by the sun. Then here we have the 2 particle analyzers, PAPA and ASPEX. So PAPA is plasma analyzer package for Aditya L1. It studies the electrons with heavier ions, and ASPEX is the Aditya Solar Wind Particle Experiment. It studies the protons with the heavier ions. Then here we have the last 7th payload, which is magnetometer, and it basically studies the changes occurring in the sun's atmosphere, sun's magnetic field, which like keeps changing in like 11 years. It almost changes to 180 degrees. And here we have the solar panels, which like collects the sun's radiations. And okay, thank you.
Sunspots will start from
Hello everyone, my name is Purna and I am an FIBSc Physics student. So in the previous posters you have seen about how solar missions are conducted and everything. Now here we will talk about planetary missions. So what are planetary missions? Why do we conduct planetary missions? Planetary missions basically we conduct because we need to unveil all the mysteries that are there in the solar system, explore other planets, and also mainly the main reason being a search for life. And when we say life, we think of something called the habitable zone. And here, what is the habitable zone? Habitable zone or the Goldilocks zone is basically an area or a region around a star where water is present in its liquid form, and also the temperature is not too high or not too low. It's just the optimum temperature for life to sustain on it. Next, because of these planetary missions, we have actually discovered some systems similar to a solar system, which is the Alpha Centauri and the TRAPPIST-1 system. And Alpha Centauri is a triple star system, unlike a solar system which is only a single star. Here, in amongst the three stars, two of the stars actually form a binary system, that is, they rotate around each other. And another star, which is the Proxima Centauri, it is located at a far distance from the two binary system. And this Proxima Centauri is actually a red dwarf, which is 10 times smaller than our sun. And some of the planets around those stars are said to be habitable, not yet proven, but said to be habitable. Next is the TRAPPIST-1 system, which is again a 7-planet system, only planet discovered till now, star discovered till now, which is consists of seven planets. And the star is also a red dwarf, and some of the planets in this system are said to be habitable, not yet proven, but said to be habitable. And some of the space agencies working towards these explorations are NASA, ISRO, ESA, which stands for European Space Agencies, JAXA, Roscosmos, CNSA. And some of the future missions planned by these agencies are Shukriyan by ISRO, Lucy by NASA, Baby Colombo by ESA. Thank you.
Hello everyone, my name is Neeraj Sanas and I am from SYBSC, majoring in physics. So as you guys heard in the first poster, which was about the planetary missions, that our solar system consists of the habitable zone, and which has 3 planets, Venus, Mars and Earth. The first one is the Venus. So coming to the first point, Venus comes on the inner edge of our solar system, and it consists of the iron core, hot mantle and the rocky crust, which is similar to our Earth, and hence it is called as the twin planet of our Earth. So then all the features do not make the planet habitable at all, but with that, the atmosphere is so dense, it consists of the sulfuric clouds which run around 471 miles per hour, which is very concentrated and acidious in nature. And the atmosphere is so dense that it could crush a person standing upon its surface. And the spacecraft like Venera 9 and Venera 13 were able to survive for just 57 to 127 minutes. Then coming to our next point, that how we were able to figure out that the atmosphere was so dense and it consists of the sulfuric acid and the surface pressure is so high that it could crush a person, is by spectroscopy. So we have explained the spectroscopy in the first graph, which we were able to figure out that specific elements or molecules which were present in the atmosphere of the Mars. This represent the atomic components of Mars, which was captured by the JWST, and which comes in the range of infrared, which is from 1000 to 5000 nanometers. So we resemble the data with the synthetic data which we had already with the data which we obtained, and we obtained this graph and the different elements present in the atmosphere. And using this, we can say the planet is habitable or not by just seeing the very tiny molecules and very minute things.
Hello everyone, myself Anadi, I am an SYBSC majoring in physics. So the second poster told you all about the inner planets, right? So here in this poster we would be exploring the moons of the gaseous giant planets. So here we have 3 moons over here, Enceladus, Titan and Ganymede. So these 3 moons, they are ice covered moons, they have icy crust, and beneath them we have an surface of oceanic water. So the first image is of Enceladus. Here it was captured by Cassini, and here what you are seeing are actually geysers of water vapor and ice particles. So these geysers, they are responsible for forming one of the Saturn's ring. Then we have next moon, that is Titan. Titan, it is Saturn's largest moon, and it is one characteristic of Titan is that it has lakes on its surface, but the lakes are not of water, they are of hydrocarbons. So as they are made of hydrocarbons, we are even speculating that they even might have microorganisms on these lakes, inside these lakes. Then we have Ganymede, which is the largest moon of Jupiter as well as the largest moon of our solar system. The oceanic waters that lie beneath Ganymede, they are so voluminous that all the oceans we have on Earth today are even less than those found in Ganymede. Next, the thing over that we have are the deep space network, which is actually used for spacecraft communications. So this network, it consists of 3 large antenna, California, Spain and Australia. These are located over there, and these 3 antennas, they actually cover 120-degree each of the sky. So in all, they cover the entire 360-degree Earth. So at any point, if a signal is coming, any of the 3 antennas catches those signals, and that's how we communicate with space. But these are in the form of radio waves, but radio waves have a limit, and that is that we cannot transmit high amounts of data with this. So in order to overcome this, we have something which is the future of space communication, that is the infrared lasers. So we would communicate with spacecrafts with the help of infrared lasers in the future. Next we have is something known as something which is a very science fictional term, that is warp drive. So warp drive, it is actually a spacecraft with which we can actually manipulate the space-time fabric, and we could actually travel greater than the speed of light. But for this we require a large amount of energy which we can't harness with the technology that we have today. So hence this is a very futuristic aspect of further space era and space missions.
Hi everyone, I'm Myra, FYBSc in Geology. In the previous poster, you learned about the various moons and the communication systems as well as about the warp drive. Now we have over here some missions as well as some futuristic missions that we have related to space science. So first, our first mission is Perseverance. The name of the I'm sorry. So our first one over here is Perseverance. It was sent to Mars in 2020 from NASA and the Jet Propulsion Laboratory. It was sent basically to collect samples and to do the data analysis of regolith, which is broken rock and soil particles on Mars. Perseverance also had on its underside a helicopter, a miniature helicopter known as Ingenuity, that was released, and it it collected various data on Mars. Next over here we have Cassini-Huygens. So Cassini's main job was to study the raging storms and the gravity of Saturn, and it's taken some very beautiful pictures that you can see over here of Enceladus and Titan as well. It orbited around, it flew past a lot of moons and as well as Jupiter and Saturn. So next up we have New Horizons. New Horizons was a mission that was sent from NASA and Applied Physics Laboratory, and its main job was to research about Pluto and its moons and also some Kuiper Belt objects. Next up we have some futuristic missions over here, such as Europa Clipper, that is going to be sent to Europa from NASA in 2024, Shukrayaan 1, that is going to be sent to Venus from ISRO in December 2024, Mangalyaan 2, that is going to be sent to Mars from ISRO in 2024, and Dragonfly, that is going to be sent to Titan from NASA in 2027. Lastly, we have SpaceX Starship. So as everyone knows, SpaceX is the largest private company that does its own aerospace missions, and it released the largest and most powerful rocket that has ever been flown. The speciality of this rocket is that it has reusable launches, and it is now renamed as the Interplanetary Space Colonization Spaceship.
Hi, I am Pritesh of FYBSc Physics. So I am here to explain Spirit. You might have learnt the last few posters. Now let's discuss about the Spirit. Spirit and Opportunity are the two rovers. We called it twin rovers. Spirit and Opportunity look the exact same, but the difference they had is one was sent to map the craters, another was sent to study the geology of the Mars. Spirit rover had found in its conquest, it found volcanic basalts, hematite, which is an abundance of water, and silica, which is a biological indicator for life. NASA honored it in the way like the site in which Opportunity landed was named after its name. Opportunity's name was done opportunity, the valley which opportunity was roaming, named Marathon Valley, because it traveled 30 kilometers around that valley. Now I will explain some components of this rover. This is a PanCam, means panorama camera. This is a spectrometer. This is a high gain antenna, and this is a low gain antenna. Rest all the black antennas are for communications. There are 2 cameras at the back also. Also we have a rat which is not included in our model, but it is in actual model. Thank you.
Hi, I'm Pratik, and my poster is on interstellar space and medium, as we come from the previous poster of planetary missions. So we see here the first poster, interstellar space and medium. It describes what exactly is interstellar space and interstellar, the medium that exists in it. Then we also see like the properties of interstellar medium. As we know now that the most abundant element that's present in interstellar medium is actually hydrogen, almost 70% of it, and it exists in different states. So my poster describes it as to how we detect it, what various methods are of detecting it in astronomy that are used, ranging from infrared to radio to visible light as well. Then after that we also study the properties of interstellar medium, by which we can come to know the formation of stars, like how were stars formed, which can provide a clue into the origin of our solar system. Then we also have molecular clouds, which are a part of interstellar medium. They are just neutral, and they consist of different really cold gases and other stuff. Then we have different kinds of nebulae that exist in interstellar medium. So there are like 3 types of nebulae. One of them is emission nebula, which emits light of its own. Then we have dark nebula, which is like an obstruction to an illuminatory source. And we also have reflection nebula, which basically scatters light from nearby sources of stars and other illuminatory sources. And yeah, those are the 3 kinds of nebulae which consist interstellar medium. Going on to next, the interstellar phenomena.
Hi, my name is Stuti Maitre. I am from FI BSc Physics. The topic of my poster is interstellar phenomenon. In the previous poster, we saw interstellar space and medium. The reason we need to explore interstellar space in the first place is because there are certain phenomena that only take place in interstellar space. We have taken example of 4 such phenomena. The first one is the heliopause. So Sun has some coronal mass ejections. Corona is the outermost layer of Sun. It ejects a ray of highly charged particles, high in energy, so high that it is able to cross the boundary of the planetary section to a distance of 18 billion kilometers. This distance marks the boundary of our solar system and thus commences the interstellar space. This boundary is called the heliopause, and since Sun is spherical and it ejects these charged particles in all directions, it forms a sphere which is called the heliosphere. This heliosphere protects us from oncoming harmful cosmic radiations, deflects them, forming the bow shock. There's also a heliosheath that lies between the point from where these waves slow down, which is called the termination shock. Moving on to the next, this is extinction. In interstellar space, when light is ejected from a star, it obviously does not follow a clear path. It collides or is passing through some interstellar dust clouds. Some of it gets absorbed, some of it gets scattered. The light that gets scattered is short blue violet. The light that penetrates is red in color, so we think the star is red and it's farther away because of less intensity, so it gives us these false assumptions. The third one is the celestial sphere, the Easter egg of this poster, because it doesn't really fit in with this category but was formed in ancient astronomy. There's an imaginary sphere onto which we take the projections of outer stars and helps in celestial mapping and location of the northern star. It is above Earth. The last one is the gamma ray burst. What happens in this is that a high energy charged beam is ejected from massive stars or black holes. Highly dangerous, it is cancer causing in fact, but passes through the heliopause, but luckily there are no such events that cause these gamma ray bursts in our solar system.
Hello, my name is Khushi and I am from Interstellar Space Interstellar Exploration Group, and I am in FI BSc Physics. So this is my poster. It's about interstellar missions, as you can see.
So Voyager 1 was the first one which has crossed our heliopause, as you might have heard it by Stuti in previous poster. So when Voyager crossed heliopause, at the time we get to know that there is something out in our solar system, and that is called as the interstellar space. We actually never knew that there is something that is out in the solar system. So when first Voyager crossed, it actually forgot its path and got accidentally out of our solar system and crossed this heliosphere, and then it get to know that there is something out of our solar system. Even radio astronomy is a part of our interstellar space, because to detect radio waves and their radio sources and from where they are originated, however where they are traveling, and how actually molecular clouds they are formed. This is what is something related to radio astronomy. So for studying this part is also taken as interstellar space. So even in this case, as you can see, in radio astronomy some radio telescopes are there, even some are ground based telescopes, and some are designed to detect it. And likewise, as you know, recent mission we are mainly focusing on is Euclid mission. So Euclid mission, it works on dark matter and dark energy survey. So what dark matter is, we haven't seen it, but dark matter is that something that is between the background of the galaxies and between us, that is not visible, but we put that there is dark matter. We just think that there is a dark matter. Actually there is, but we haven't seen it. So for studying this purpose, we use gravitational lensing. There is a bending of light phenomena, and now even baryonic acoustic oscillation is used. So what happened in baryonic acoustic oscillation is that when Big Bang happened, after 300,000 years after the Big Bang happened, Dark Ages phase was there, and in this phase there was nothing formed because the universe was smaller and the temperature was too much higher. So for this formation, a coupling process happened between neutrons and protons, and neutrons and protons are called as baryons, and when this coupling process happened, sound waves were produced. These sound waves are called as baryonic acoustic oscillation. Now that it is formed because of baryons are made up of 3 quarks, and Astro because of sound study. Thank you.
Hello, my name is Stuti Sharma, and I'm from FI Physics department. And in the earlier poster we read about and we know about the interstellar probes and dark energy and dark matter. In my poster we'll talk about neutrinos. So neutrinos, they are elementary particles and they belong to the class of leptons. They are incredibly small, electrically neutral, and they have extremely low mass. They are detected from astrophysical sources such as supernova, cosmic rays, and from sun's core. So neutrinos, they are present in 3 flavors, which is our electron neutrino, muon neutrino, and tau neutrino. So as neutrinos, they travel through space, they morph into 3 different flavors. This happens because the neutrinos, they are present as a combination of 3 mass states. So to detect these neutrinos, we have 2 observatories, which is Super Kamiokande Observatory and Ice Cube Observatory. The Super Kamiokande Observatory is situated in Japan, and it's a very massive water tank which is filled with 50,000 tons of water, and the ice cube is actually embedded underneath the ice in South Pole. Both of them work on the same principle, that when neutrinos travel through space, they collide with the water molecules, and those charged particles that are ejected, they travel faster than the speed of light in that medium, and they emit a blue light, which is called Cherenkov radiation. And we are actually able to detect that light with the help of the sensors which are present, and this light gets detected, and that's how we know a neutrino was present. Thank you.
Good afternoon, I am Tejas Chandran. I am here to explain this model. Basically, this is a neutrino observatory. Neutrinos, as you know, is part of an elementary particle, elementary group of elementary particles. So it doesn't have any mass, and it is also neutral. So in order to detect them, it is really hard. So we have designed these neutrino observatories using this is a Super Kamiokande one, and that one over there is actually ice cube. And what happens is that these are buried deep inside the ground, and these are massive water tanks filled with water. And when the neutrino is incident on it, can you post it? So like when the neutrino hit the water, it ejects either electron or muon through W interaction, or otherwise it will elastically collide with an electron, releasing an electron. So these electrons and muons that are produced actually travel faster than light in the medium, and so it produces Cherenkov radiation. So that is what we detect.
Okay, hi, I am Purva Kulkarni and I will be explaining you JWST, which is James Webb Space Telescope, which is sent to the space behind the Earth at the Lagrangian point 2. There are actually 5 Lagrangian points and it is at L2. So to know about this, it is the advancement of Hubble telescope. If we have seen the images of JWST, they are much clearer and we can get more information from them. So these are the sunshells. So these sunshells are at the size of the tennis court. There are 5 sunshells. So why sunshells? The radiation which is coming from sun gets absorbed by the first layer, and till the 5th layer the radiation gets reduced, so that the telescope won't get damaged. Then you have hexagonal shape mirrors. Why hexagons? Due to the packing efficiency. So packing efficiency of the hexagon is maximum. We use gold as the... Why did we use gold? So gold is 99% reflector of the radiation. So as the parabolic disc, it also acts at the reflector. So 99% radiation gets reflected back to the surface, to here, and then it gets back to the antenna. Then at the back, here black box is there, the analog signal gets converted into a digital signal, and it gets sent to the Earth, and we can get the data and we can predict the images from it.
Good afternoon, I am Shavalika Sharma, FY BSc Physics. So now that we have learnt about interstellar mediums, I will be introducing the concept of gravitational waves. By far, we have observed gravitational waves as a force, and we have studied about gravity as a notion of force. Now I will be introducing gravity as a wave. In 1916, Albert Einstein introduced gravity as a wave in his general theory of relativity, where he explained that gravity is not actually a force but rather a deviation or a distortion in the fabric of space-time. Gravitational waves are undulating waves which travel in the fabled fabric of space-time from the source to our observatories here on Earth. They have a very high magnitude, and by the time they reach Earth, this magnitude dies down significantly. So to put it in perspective, the waves that we observe on Earth are, for example, if you take the distance from the sun to the Earth, the waves that we observe would be the thickness of your hair strand. So the magnitude is very, very tiny. Gravitational waves are primarily categorized into 4 types: continuous, compact binary in spiral, burst, and stochastic. Till now, the major observations in the major study has been done on compact binary in spiral waves. These waves are categorized into 3 subtypes depending on the type of binary that they are in. And we have stochastic waves, which is a merger of a lot of smaller magnitude gravitational waves, on which we perform Fourier analysis and we get a graph similar to this. Gravitational waves have other sources as well apart from binaries, such as pulsars, black hole mergers, supernovas, and other cataclysmic events. They have various properties. They travel at the speed of light. They have 2 polarizations, H plus and X cross. That means that they have 2 maximas and 2 minimas at the same time. Apart from this, studying and observing gravitational waves tells us about a lot of events that are not observed in other spectrums, like dark sirens, exotic merger of bodies, and other compact objects which do not have an EM or a radio counterpart. Thank you.
Hello, my name is Ishita Chatterjee and I am an FY BSc Physics student, and today our topic is gravitational waves. In the previous poster, you saw what they were, what the different kinds were, what the different sources were, and what the different properties were. But let's talk about how we can detect them. So here we have LIGO, which stands for Laser Interferometer Gravitational Wave Observatory. It works on the basic principle of interference of light. So here you can see the instrumentation. You have a laser, a light source. You have a beam splitter. You have mirrors here and here. And you have a photodetector. So the light leaves the laser source, passes through the beam splitter, and is split into 2 arms. These 2 arms are of the same distance. So the light waves end up traveling the same distance, as a result of which there is no path difference, there is no phase difference. So when they hit the photodetector after interfering with each other, there is no interference pattern. In fact, it is dark. But if a gravitational wave were to pass through it, one of these arms would be lengthened and the other would be shortened due to them being quadrupolar waves. So the path obviously changes and there's a phase difference. So we achieve a interference pattern on the photodetector and we know a gravitational wave has passed. There are different gravitational wave instruments around the world. We have LIGO Hanford, LIGO Livingston, Virgo, GEO 600. Each of these are capable of detecting gravitational waves and they exchange their data and compile a waveform which confirms that a gravitational wave has passed. There are several other components also in it. The laser, which starts off at 4 watts, eventually becomes 200 watts and it is an infrared laser. Of course, we also have a vibration damping system which is used to eliminate any vibration that may interfere with the light waves. We also have a vacuum which is 1 trillion the atmospheric pressure at sea level. This is done to reduce Brownian motion and to remove any particles interacting with it. And of course we have mirrors here which are ultra high purity fused silica mirrors which are capable of only absorbing 1 in 5 million photons. So yeah, that was all about LIGO.
Hello, I am Kshitij, I am TYBSc students. Now we are going to see how gravitational waves can be detected. So here we are seeing a LIGO model. So this is the observatory where gravitational waves are detected. So first we are going to see what is LIGO full form. LIGO stands for Laser Interferometry Gravitational Wave Observatory. So coming to the 2 arms of the LIGO, these are 4 km long arms based on the Michelson interferometry principle. So here we have a laser source which will emit infrared laser beam. Then we have a detector here. Also, when laser comes through a laser source, it will split by a beam splitter in 2 directional perpendicular to each other in a 90 degree, and they will travel through the 2 arms of the LIGO. And here we can see there is a system quadrupole pendulum, and there they have the test mass over there, and the laser travels through the transparent mirror. The transparent mirrors have the very high reflectivity. It's like then the laser comes to the quadrupole pendulum, the test mass, and then reflected back. So how we detect the gravitational wave? Let's imagine a gravitational wave comes to the earth. Then when it passes through the earth, there is a slight change in the arm length of the 2 arms of the LIGO. So if it's disturbed in the 1 arm, then the path difference created in the laser beam transmitted in the laser beam coming in the 1 arms, and due to the path difference created at the detector, interference patterns are created. So through that interference pattern, we detect the gravitational waves are coming, and it is coming from the source. The source are like compact binary objects like black hole mergers, black hole neutron star mergers, or neutron star mergers. So this is how the LIGO works on the Michelson interferometer principles. And the most important thing is how sensitive it is. If you it is so much sensitive that if you take a distance from Earth to Sun, the sensitivity or the change of magnitude is the only thickness of your hair. So that much of sensitivity we are detecting through the LIGO. So welcome, thank you.
Okay, so in the last poster you got to know about what are pulsars and all. Here we will see what are the applications of pulsar. So one of the major application of pulsar is the pulsar timing array or PTA. So what is pulsar timing array? Pulsar timing array uses a set of pulsars and also a set of radio telescopes spread across the globe for the detection of gravitational waves. Now how exactly does this pulsar timing array detect gravitational waves? Now consider the tip of my pen as the lobe of a radio telescope, and consider this pulsar. Consider this thing as the beam of pulsar. Now whenever the pulsar aligns with the radio telescope, the time of arrival of the pulsar to the radio telescope is noted. As you know, whenever a gravitational wave passes, it will either compress or stretch the space-time. Hence, the compressed or stretched space-time will indirectly change the distance between both of these, and hence will affect the time of arrival of the pulsars. The difference between those 2 timings will give us the idea that yes, a gravitational wave has passed and we have detected a pulsar, and hence we have detected a gravitational wave. Okay, So about pulsar timing array is that why do we need this? We need this because for the detection of lower frequencies of gravitational waves. Using LIGO we detect the higher frequencies, but using pulsars we detect the lower frequencies of gravitational waves in the range of 10 raised to minus 10 to 10 raised to minus 6 Hertz. And one of the highest achievement of this pulsar timing array is the close prediction to the detection of this stochastic background, which was released by Nanograph in the year 2022. Here you could see the alignation of both these curves, which shows that yes, we are close to our detected value and we could have detected the stochastic background.
Start. Hi, my name is Sagnik De. I am from SYBSC. You must have heard about the pulsar timing array. So this is the model. So basically in this model we have one pulsar that is supposed to be spinning, and we are supposed to have another pulsar. Basically in a PTA we take a set of 40 pulsars, 40 millisecond pulsars that is, and we take readings from them using multiple radio telescopes across the world. So basically if you can see here, the pulsar, one second, the pulsar is spinning like this. Yeah, like this multiple pulsars will spin, and as you can see these are the magnetic poles of the pulsar. Basically the magnetic field that the pulsar generates, the neutron star generates, the poles of the pulsar will emit pulses which are then detected by the radio telescopes on Earth. By the lighthouse effect, when the poles align with the radio telescope, different time of arrivals are noted. Basically the time of flight is the time taken for the pulse to come from the pulsar to the Earth, and then when it arrives we call that the time of arrival. If a GW passes in between, that causes a change in time of arrival. So thus we have multiple readings, T1, T2, T3 and so forth, and the difference between them tell us the existence of a GW. So these are all the different PTAs. The Nanograph in North America, this is PPTA in Australia, this is InPTA in India, this is EPTA in Europe, and this is CPT of China. Thank you.